We're in a unit called counting, but we're going to take one section and go over something that might not seem like counting. We're going to learn about the bijection rule, and then we'll be able to use that rule later when we're trying to find out how to count the number of ways certain things can happen. Okay, so first of all, for the bijection rule section, we need to define the term inverse. And I'm sure you already are familiar with this in terms of functions. So here's what this says. The inverse of a function f that maps a set S to a set T, S would be the domain, T would be the range, is a function G that maps T back to S. So we go from S to T, and then G would take us from T back to S, such that for every element in S and every element in T, S being representing an element in S, little s would represent an element in the set S, and little t would represent an element in the set T. F of S equals T if and only if G of T equals S. So F and G would be considered inverses. If we put something into F and we get something out, and we put what we got out into G, and we get back to what we started with. Okay, F of S equals T if and only if G of T equals S. If a function f has an inverse, we'll usually call it, instead of G, we'll call it f with a -1 up there, which means that's the inverse of f. So let's look at an example here. Let's say that we have a set S with the elements A, B, C, and a set T with the elements Q, R, S. And let's say that we have a function we're calling f, and it maps these different values in S to elements in T. Okay, so let's say that we have it set up so that A maps to R, B maps to Q, and C maps to S. Okay, if that is our function f, we see that we have elements from S being mapped to elements in T. Now let's look at a possible inverse. Let's call it G. And if we have this going on, where R maps back to A, remember A mapped to R in F, and now R is mapping back to A. And then Q maps to B, B mapped to Q in F, and now Q is mapping back to B. And S maps to C, C mapped to S in F, and now S is mapping back to C. So if that is, we're going to call it G, and if that's the mapping for that, then we would have to say that those two are inverses, right? Now here's another example, though, of a function that would not have an inverse. So if we had a function f where A mapped to R, B mapped to Q, and C also mapped to R. Remember, we can consider that a function because we don't have the same, we don't have some element in the domain that is connected to, that is mapped to two different elements in the range. Remember, that's what would keep it from being a function. But that's not the case. It's just that we have an element in the range that have two mapping to it. So that would not have an inverse, because if we tried to map from R back to the original, where we got R from by starting with the domain value, we'd have to say, well, A got us to R, and so did C, and so we can't come up with a function that would be able to be an inverse of this. Now here's the word bijection. A function f from a set S to a set T is called a bijection if and only if f has a well-defined inverse. Okay, so it's basically just a function mapping from one set to another. But if that function has a well-defined inverse, we can call that a special name, which is a bijection. So let's look at an example. We're going to create a bijection from a power set to a set of binary strings of length 3. Let's say that X has 3 elements, R, S, and T. X is a set with 3 elements, R, S, and T. And then if we were to find the power set of X, that would give us what we have over here. We usually call that capital P of X, and this is a set of all of the subsets of X. So remember, the empty set is a subset of X. This set here with just an R in it, that's a subset, and you can look and see all of those are subsets of X. And notice at the very end we have the set RST, which is the actual set X. But remember, a set is always a subset of itself. Okay, now let's call the elements in X, X sub 1, X sub 2, X sub 3, just so that we can refer to them, as the, first element, second element, third element. Now, here's what we're going to do. We're going to try to create a function that will map these subsets in P, in the power set of X, map each subset to a binary string of length 3. Okay, so let's read this and you'll see it ends up being a fairly simple concept. For each subset of X, it says each Y subset of X, but let's just think of it as for each of these subsets that are showing up in the power set, those would be subsets of X. And so we'll call those individual different sets, we'll just say capital Y is one of those sets. So, but for each of those, then the function f of Y, so it's going to map a set from the power set into a 3-bit string. Then it says let f of Y be a 3-bit string Y whose bits are, and we're going to name them Y1, Y2, Y3, just so that we can refer to them. Now, here's the bijection that we're going to create. The string f of Y is defined by this rule. Y of I equals 1 if X of I is in the set. Otherwise, Y of I is equal to 0. Now that might seem a little confusing, but basically it's saying that if we take a look at any of these sets in the power set, if the element, we're going to have 3 slots, and if the corresponding element from X shows up in this subset, then we'll put 1s in the place of corresponding to the particular elements that are in there. Let's see an example. It'll make a lot more sense when we see this. So Y, all of the different possibilities for Y would be this, right? These are all of the subsets of X. Then we're going to map each subset into a binary string of length 3. Well, first of all, let's look at the first one, the empty set. No elements are in the empty set, so we would say that no elements from X are in there, right? So what we could do is just define the 3-bit string that goes with that set as 0, 0, 0, meaning again that each bit represents whether or not the original element from X is in this subset. Let's go on to the next one. If we look at the subset just containing R, which was the first X sub 1 in X, first element listed in X, R is in there, right? R is in this subset, but S and T are not. So we would put a 1 for the first bit because that's saying that R is in this subset, but S and T are not, so we would put zeros for the next 2 bits. For the next one, S is in this subset, and that was the second one. That was X sub 2. So we're going to have Y sub 2 equal 1, and the others would equal 0. So that's saying that the second element in X is in this subset. And T, it's the third element in X that's in that subset, and the others aren't there. Now R and S, those are the first 2 elements in X, and they are in this subset, so we put 1s there. For RT, we'd have a 1 and then a 0 for the S slot, and then T we'd have a 1 for that last slot. ST would have 0, 1, 1 because R's not in that set, but the others were. And then RST, every one of those original elements of S are in this subset, so we would have a 1, 1, 1. Okay, so basically it's a matter of, just putting 1s wherever, for each subset. If that element, the original element, shows up in the subset, then we're going to put a 1. Otherwise, we put a 0. Now we can go back the other way, right? Because I could always, if I started with f of y and just started with these 3-bit strings, would that give me the correct subset? Well, yeah, because let's look at maybe the first one, 0, 0, 0. Well, if I still have this rule in mind, that would mean the subset I'm thinking about has none of those original elements in there. So that would then lead me to conclude that, if I'm going backwards, that would lead me to conclude that the set that corresponds to that is the empty set. Let's just look at the second to the last one, the one with the S and the T as in the subset. But let's look at the number, the 0, 1, 1. If I just looked at that, let's see, will that get me back to this subset ST, knowing this rule? It would, because I'd just say, well, there's a 0 in that first slot, so that means that R is not in there. But there's 1s in the second and third slot, so that means that S and T are in there, and so that would lead me to this, back to this correct subset, right? So we see that there's a clearly defined mapping such that we go one way and then going back the other way, using the same rule, we end up with the same thing. So, so the inverse of F maps binary strings of length 3 back to those subsets of X. So we would say, there's a clearly defined inverse here. So therefore, we could call it a bijection. So we could say this is a bijection from the power set of RST to the set of binary strings of length 3. Again, it's because, we might think this is so different. We've got a power set of we've got a power set, and then we've got these 3-bit digits, 3-bit numbers, binary strings, and how can we come up with a correspondence there that could basically be a bijection, and we see that just by that simple rule we've been able to do that. So let's just try to see if we can make sure we understand this. What would F, as long as we're still using this rule here, what would F of the set containing RT be? Well, we'd look up at X and see that R and T are the first and third elements listed, so then the number then would be 101. What is the inverse of 0, 1, 0? Well, that would mean that R is not in there, but S is in there, but T is not in there. So it would be just the element that has the S. How many elements are in F inverse of 0, 1, 1? Okay, we wouldn't even have to try to figure out which elements those are. We see 2 1s in there, so we know that there would be 2 elements in that. Okay, so that's kind of how to go back and forth here. And I think the participation exercises will have you working with this, and maybe even the challenge exercises too. So now let's talk about the bijection rule. So we know that we've just created a bijection here, and so let's see if after we learn about the bijection rule, let's see if this seems to work for this example. So the bijection rule says this: let S and T be 2 finite sets. If there is a bijection from S to T, then the number of elements in S is equal to the number of elements in T. Okay, so let's think about this here. In this example, that would be saying, since we found a bijection from a power set to these binary strings, this would have to tell us that there are the same number of elements in each set. And it's true, we could just count them. We could count the number of elements in the power set and the number of digits in those number of different binary strings, not the digits, but the number of unique binary strings, and we would see that the number is the same. And just that notation there, where we have the 0, 1 in curly braces with a 3 above it, that just is trying to say that's binary strings of length 3. That's kind of a different notation, but that's what that's saying. And what would that be here? Well, see, here's the deal. We know how many sets of binary strings of length 3 there are from that product rule that we just learned, right? Because we could think of 3 slots and how many choices for the first slot, how many choices for the second slot, how many choices for the third slot, right? And that would be 2 times 2 times 2, which would give us 8. So the thing is we can find the number of binary strings because we have that product rule to go by. So what we're going to be doing, and this is kind of why we're even talking about this, is that we can translate the situation where we're trying to find subsets, the number of subsets. We can use this bijection and say, well, I don't know that. I don't know how many subsets there are, but I could find the number of binary strings of a certain length. And then we see that we could make this bijection for any size of a set, and therefore we would know that all we have to do is find the number of binary strings of that length, and that would give us the number of subsets. Okay, so this gives us a way of counting subsets. Now there's another definition that we're going to be using later when doing some counting. And so I'll go ahead and go through this. It's a pretty easy concept. The definition is called, it's a K to 1 correspondence. Let's say that X and Y are finite sets. The function f that maps X into Y would be considered a K to 1 correspondence if for every element in Y there are exactly K different elements in X that map to it, such that f of X equals Y. So in this example here you see X is just the numbers from 1 up to 11, and then some of those numbers map to 0, some map to 1. And so So we would say, if we counted, we'd see that 6 elements map to 0 and 6 elements map to 1. So we would say that this function, if we're going to call it f, we'll call it f, is a 6-to-1 correspondence. Okay, so now here is a rule called k-to-1 rule. Suppose there is a k-to-1 correspondence from a finite set A to a finite set B. Then the number of elements in B is equal to the number of elements in A over K. And remember, K is part of that k-to-1. Okay, so this is basically something that is pretty trivial in a sense that you would know this. If I said, well, here's an example. This is a 6-to-1 correspondence between X and Y, and there's 12 elements in X. How many elements do you think there are in Y? You'd probably say, well, 6 of the elements in X go to one, 6 others go to the other, so there must be that 12 divided by the K, which is 6, and that would give us 2. Okay, so anyway, it does work for this problem, right? So F is a 6-to-1 correspondence, as we have here, and sure enough, the number of elements in Y, which is 12, equals, sorry, no, the number of elements in Y is 2, right? And that equals the number of elements in X divided by 6, which would be 12 divided by 6. So we see that it works here. Now we'll move on, and we're keeping those two rules in mind, the bijection rule and the k-to-1 correspondence. Okay, so when we're interested in this section in counting the number of subsets. A subset of size R is called an R subset, sometimes referred to as an R combination. And if you've had statistics, you've learned about permutations and combinations. And combinations are different than permutations, but that is the context here we're talking about for combination. So if you do have that experience, then that is what we're talking about here. But for those of you who haven't heard of a combination, first of all, then just think about this as we're just talking about subsets of size R. So let's take this set A that has elements A, B, C. List all of the 2 subsets of this. And so remember, if a 2 is in front, that means we want subsets of size 2. So we could just pull them out. AB, that's a set with 2 elements, and it's a subset, AC and BC. Now, you might say, well, why didn't I list BA and CA and CB? But remember, if we're talking about sets, the order doesn't matter. So if I have the A and the B in the curly braces, that just means this is a set that includes these 2 elements A and B. And so if I had changed that and put the B first, as you see at the end of the sentence, that still doesn't change the set itself. The set is still the set that has the 2 elements A and B. So with sets, the order in which the elements are listed doesn't matter. So that's why we would not go ahead and list these sets with the elements in a different order, because we'd just be listing those same sets over. Now let's try to talk about this in the context of this unit, and that is counting the number of a number of situations that could happen under certain requirements. If we need to form a committee of 3 members from a class of 25 students, we would be forming a 3 subset, right? It's a subset of 3. We wouldn't be distinguishing an order at all, right? And we're not saying vice president, and so on. We're just saying we want a committee of 3. So if you think about it, then getting a committee of 3 members out of a class of 25 is just getting a bunch of subsets that have 3 elements in them, 3 students in them. So we're just looking for subsets. If we wanted to find out how many, we'd be saying, if we were asked how many different committees could be formed this way, we'd be asking really how many 3 subsets are there of this, right? Okay, so oh, and then this is just a reminder here. Again, as I said, we're not distinguishing in order, so therefore the number of ways to form the committee is not going to be it's not going to be the same as the number of ways to assign a president, vice president, and treasurer, right? Because I just want members of a committee, so I don't care. That's just a set of 3 people, and they're not ordered. So that's what's going to be different here than from permutations, because with permutations we'd be saying how many different ways can we pull out 3 members of this group and give them the offices of president, vice president, and so on. But we're not doing that. We're just saying you're either in the committee or not. So that's why it's just purely subsets. Okay, so now we're going to try to see if we can find out a way to count the number of subsets from a set. And we're going to end up using the K to 1 rule. Okay, so let's say that we have a small set S, which is just the elements A up through G, and we want to take subsets of size 3. Well, let's say that we don't have a formula yet for that, but you could say, I don't know the answer to this, but how many subsets of size 3 there are, but I could find the number of permutations, right? Because we've already done that before. We learned that rule, and remember that permutation rule would be taking, here we would be taking 7 things 3 at a time, right? So if we were looking at permutations, then we would be doing a permutation 7 things 3 at a time, which would be what you see over here at the right, 7 factorial divided by 4 factorial, right? Because that was the formula for permutations. Okay, so that would give us the number of permutations. Now that's probably not what we're going to be asking for, because it says we're counting subsets here. So we're eventually going to be asked how many just plain subsets are there, not permutations. Well, let's define a mapping from all 3 permutations, meaning permutations of 3 elements out of that set, to 3 subsets, meaning all subsets of 3 elements of that set. So we're defining a mapping from the permutations to the subsets, each of size 3. So how would that function be defined? Well, we could just say each permutation, let's just map it so that the order just becomes removed. So like the permutation A, B, C, where A comes first, then B, and then C, that would map to the set of those elements A, B, C, right? Where we don't care what what the order is in that second, in the curly braces, because again it's a set, so it's just saying elements with those 3. So the permutation with A first, then B, then C we could say would map to that set, but also the permutation BAC would also map to the set if we've just defined this function as removing the order. Okay? So how many permutations would map to the selection ABC? Well, we'll just think about it here. We would have the permutation ABC, ACB, BAC. We would just think of all of the different ways we could order those 3 elements, and there's actually this many There's 1, 2, 3, 4, 5, 6. There's 6 different permutations would map to just that one set. And, that number 6, we could have found that by finding the permutations of 3 things taken 3 at a time. And that gives us the, 3 factorial over 0 factorial, which is equal to just 3 factorial, which would be 6. Okay, so what we've done so far is we've defined this function where we're taking all the permutations and having them mapped to just the set that includes those elements. And think about this, we used A, B, C, but there's other elements in S. So I could take any other subset of size 3, E, F, G, let's say, and I could do the same thing as I did above here. I could say, well, EFG could be, would have, how many EFG, how many permutations would there be of those 3? And we'd see it's the same number, the permutations of 3 things taken 3 at a time, which is again 3 factorial. So no matter what the 3 elements that we are interested in, we see that we would always get 6 permutations for each subset of size 3. So we would say that the function is 6 to 1. I have here, I say that function is 3 factorial to 1, just because the permutation was found by 3 factorial. But, we could probably maybe better say it as a function that's 6 to 1. Okay, 6 to 1. So now we're going to use the k to 1 rule. So let's think about, remember what we're trying to do is find out how many subsets there are of, in this case, just these 7 elements. Okay, well, we will use the k to 1 rule, which says this, that the number of subsets of this set is equal to the number of permutations divided by 3 factorial, because remember the 3 factorial is the k, and we said, so if we have this correspondence, 6 to 1 correspondence, then I could take the number of the set with the more values, which would be this the permutation 7 things 3 at a time, and divide that by k. Okay, so let me say this again, because I may have I'm not sure if what I said was confusing or not. Remember, what we're trying to do is compare the number of subsets of size 3 to the number of permutations of size 3, and we know that's k. It's for each set of 3 letters, it's a 6 to 1 relationship. So therefore, we would say that how we would count the subsets would be take the number of permutations and divide it by this k, which is 3 factorial. Anyway, so if we do that, all we did again was take the number of permutations divided by 3 factorial, and we're saying that gives us the number of subsets because we know of this 6 to 1 correspondence. What would that be? Well, permutations 7 things taken 3 at a time would be 7 factorial over 4 factorial. But now I divide by a 3 factorial. Now I put this kind of in, you might think this is a strange way of looking at it, but this would be the way we would need to do it algebraically in order to come to the conclusion of what you see here at the very right. If I take this permutation and divide it by 3 factorial, that's the same thing as dividing it by 3 factorial over 1. But remember, when we're dividing by a fraction, that's the same thing as multiplying by the inverse of the fraction. So I'm going to flip this bottom fraction over, so the ones at the top, the 3 factorials at the bottom, and then multiply. And hopefully you see that that's how we would end up with the 3 factorial in the bottom with the 4 factorial there. So by dividing by 3 factorial, it just ultimately just puts that 3 factorial in the denominator along with the 4 factorial. So that would be the number of subsets, number of 3 subsets, meaning subsets of size 3, of this 7-element set. So we've looked at this as just through one little example, but ultimately we want to talk in general about how do we find, if we can find the number of permutations of something, which we said we could find already. We already know how to do permutations. We want to be able to come up with a general rule so that we could find the permutations and then do something to that to then come up with the number of subsets. And we see that we did it here with this one example. We found that it was just the number of permutations divided by whatever that correspondence, the K was in the correspondence. And so we did that. So let's see if we can talk about this in general. So in general, when we're choosing subsets of size R from a set of size N, the K that we end up getting, if we were looking about, as the last example, we mapped permutations to subsets. Remember that last example? We ended up with 3 factorial. It turns out that K is always going to be what would be the R factorial. Remember, R in our last example was 3, and we did see that K ended up being 3 factorial. So anyway, the K ends up being this R factorial. So in going from permutations to subsets. So if we're trying to count the number of subsets in general, then we would count the number of permutations in general, n things R at a time, and then divide by R factorial, because again the R factorial is the K, and that we're using the K to 1 rule. So that gives us a nice little formula here. So here in this box, definition, counting subsets, n choose R notation. So remember what permutations, we would say things like the number of permutations of n things taken R at a time. What we usually do now when we're talking about just subsets is we could say, well, here usually we'll just say something like n choose R, meaning we start with n things and we choose R at a time. But we're not looking at permutations, so we don't say anything about permutations. So we would call this n choose R, and we'll use this. You see this notation here with the n and the R in these big parentheses. N is on top and R is below. That is represents that we're taking n. We're starting with a set of n things, and we're taking R at a time, and the fact that it's in those parentheses means that we're talking about the number of subsets. Okay, so the number of subsets of n things taken R at a time is equal to, and you see here that first of all this n factorial over n minus R factorial, that's just the formula for permutations, but then we divide it by R factorial, which is what we saw that we would need to do. So this is just the permutation function formula with the R factorial down there underneath. And they have this R factorial first. It doesn't matter if you would list it second there. Sometimes you see it listed second. But anyway, that's would be the formula for finding the number of subsets. Again, this says that the n over the r in these big parentheses is read n choose r. But sometimes we'll use this notation because you remember we're using the capital P for number of permutations with the n and the r in there. So sometimes you'll see it this way with the capital C, n and r. So capital C with the n comma r means we're taking subsets. We want the number of subsets of n things taken r at a time. And that is easier to type than the n and the r in those big parentheses. So what you'll be doing, what zyBooks will ask you to do, is in some cases answer questions in this by using the capital C and then parentheses and then put the correct numbers in there. So that's how they'll like you to answer questions. So let's see if we can calculate 7 choose 4. Again, that's the number of subsets of 4 items out of a set of 7 items. Well, we'll use this formula up here. And so it would be 7 factorial on the top, and then 4 factorial on the bottom, and then times 7 minus 4 factorial also on the bottom. So really, again, it's just the permutation with this extra 4 factorial down there. So now I'll just simplify that 7 minus 4 to give me a 3. So I've got 7 factorial over 4 factorial times 3 factorial. We can do some simplifying here. Write out the 7 factorial and stop at some point so that you can have something to cancel out. We'll stop at the 4 factorial so we can cancel out the 4 factorials because we would have one on the top and one on the bottom. And then let's write the 3 factorial is 3 times 2 times 1, and then we could cancel out the 3 times 2 down at the bottom with the 6. And so then we have an easy calculation. It's just a 35. So with these combinations here where we're doing this, where we're finding the number of subsets, your calculations are very simplify very quickly by just doing this simplifying here. So here we ended up being able to do this all in our head without even having to pull out the calculator. So that's why it's good to know how to do this kind of thing here, where you just do canceling and then end up being able to come up with something easy, because then you don't have to use a calculator. Okay, let's look at that 9 choose 3, or I would say a combination of 9 things taken 3 at a time. Number of combinations, 9 things taken 3 at a time. Okay, well, we'll use the formula. It's 9 factorial over 3 factorial times 6 factorial, because 6 I get from the 9 minus the 3. And then again, let's write 9 as 9 times 8 times 7 times 6 factorial. The 6 factorials cancel. Then I'll write the 3 factorial again as 3 times 2 times 1 down there in the bottom. And now we can do some canceling. The 9 at the top and the 3 at the bottom can be canceled, leaving us with a 3 on the top. And the 8 over 2, the 8 and the 2 can be canceled, and that leaves us with a 4 on the top. And then now that's it. We don't have anything else left on the bottom except for 1. So it would be 3 times a 4 times a 7. So it ends up being a 12 times 7. And that would be our answer. And that would end up giving us an 84. One thing I wanted to point out, just to cut, because it's a kind of a nice little way to verify, make sure you're remembering the formula correctly and make sure you're putting the right numbers when you do problems like this. Look at this bottom one here, the 9 choose 3. Notice we know that to start with a 9 factorial on the top. And then the choose part was a 3, right? And notice what I did. I started with a 3 factorial. So you'll always, the number on the top goes up on the top with a factorial, and then on the bottom you'll just take that bottom number and add a factorial after it. But then you have one more, and what that's going to be is another factorial. But here's what I always do when I write that out: just verify that I did it right by making sure and see if I take these two numbers down at the bottom, but not worry about the factorial. So in this case, it would be a 3 and a 6. If I add the 3 and the 6 together, I do get the 9. So it's basically you start with what's on the top, put that as the top with factorial, then take what's on the bottom, put that down at the bottom with a factorial, and then come up with that other number so that when you add it to the 3, you would get the 9, and so we know it's a 6. Anyway, you're using the formula, but it's just a quick way to make sure that you haven't made a mistake. So let me go back up to the problem before, and let's look at the 7, choose 4. Let's look where it says 7 factorial over 4 factorial times 3 factorial. So it's that second step there. Again, we'd say we could have gotten to this right away by saying, well, 7's on the top, so I'm going to put a 7 factorial on the top. 4 is on the bottom, so I'll put a 4 factorial on the bottom. Now, what do I need to add to 4 to get me back to 7? It's a 3, so I need a 3 in here with a factorial, and that'll get me my formula. And so then we'll end up getting the answer eventually. Now, you won't have to have these memorized because you're taking this, you'll be taking tests remotely, and so I'm not going to say that you can't use your notes. So you don't have to have these memorized. Of course, what usually happens is if you already know them, it can make it, of the times that you have to come up with these numbers, if it's probably easier to take a moment to try to memorize it and then be able to use that and pull it up yourself anytime you need it. It's probably more efficient to do that than to not memorize it and then have to look it up each time. So I'd suggest it wouldn't hurt to memorize this. Okay, so now let's get back to the type of questions that we're going to be answering here in counting subsets. So here we saw this question already. How many different ways can a 3-member committee be chosen from a class of 25 students? Well, we would see that is we're finding subsets of size 3 from a class of 25. So we know we would recognize that as a combination problem where we would be taking 25, choose 3. And we remember our formula that's the same thing as what we'd have with the permutation, but then with the extra r factorial down below. Or again, you could just use that formula that you've memorized. So we'd have the 25 factorial on top, 3 factorial on bottom, along with the 22 factorial, because we got to double check, does 22 and 3 give us 25? And it does. Okay, now we'll write out 25, but stop at 22 factorial, so we can cancel the 22 factorials. Then the 3 times the 2 is a 6. That can be canceled with the 24 up above, becomes a 4. So we end up with, at least you might want to get your calculator out at this point, but at least you don't only have 3 things to multiply. 24, well, no, we wouldn't have to use our calculator here because 25 times 4 happens to be 100. That's an easy one. 25 times 4 is 100, so 100 times 23 would give us 2300. But if it hadn't happened to been that way, and maybe it was a 23 times 4, something like that, then you would want to get your calculator out. But this one we could have done in our heads. So anyway, the answer is 2300. So there's 2300 different committees that could be chosen out of a class of 25 if we have 3 members on each committee, which is kind of crazy, right? It seems like it shouldn't be that many, but there are that many. Now here we're just going to make an observation. Think about if we were trying to find 6, choose 2. that would be 6 factorial over 2 factorial times 4 factorial using this formula up at the top right. If I were looking for 6 choose 4, I would get 6 factorial over 4 factorial times 2 factorial. But if you take a look at those denominators of those two fractions, it's just the same factorial is just written in a different order. And since that's multiplication, the order doesn't matter. So that will turn out to be the same number. So in general, here's what ends up being true, that n choose n minus r is equal to n choose r. So, and here's the official proof for that. You could just plug in the numbers for using the formula for n choose n minus r, and then do some simplifying and find out that that ends up giving you the same thing as n choose r. Now, it's not that you necessarily have to use this, but sometimes you might be doing problems and you do two different problems and you see that you get, two different steps maybe to the same problem, and you see that you got the same answer, but it was a different combination value you were looking for, and then so you might think, wait, I must have made a mistake. But it's just helpful to know that, no, this is what happens. Sometimes you actually end up with the same answer when you do different combination problems with the same top number, because that's just the way this works. Earlier in this lesson, we came up with a bijection in order to come up with that formula for the combination, right? Remember, we said, well, let's consider that a power set of a certain set and see that there's a bijection between that and some binary strings. Then we were able to talk about how we could come up, how that there would be the same number of binary strings as there were these subsets, and then we were able to develop that formula for the combinations. Anyway, we're going to be using a similar bijection now, but we're going to be talking about something else, learning how to do something new. So let's say that we're asked to count the number of 4-bit strings that have exactly 3 ones. So look at here in this little picture, we see all of the different 4-bit strings that have exactly 3 ones. And let's consider a bijection similar to what we considered before, that we've got these sets of size 3 that correspond to those binary strings, in the sense that if there's a 1 in a certain slot, then that corresponding set is meant then to be part of that subset. So for this first line here, the first 3 digits are 1, and so that would mean the first 3 elements of this set, A, B, C, make up the subset. The last one here, the first one is 0, but then the next are 3. So that would correspond to the subset B, C, and D. Okay, so we are going to come up and say that, yeah, here's a rule. We see that it is a bijection because it's a function going from the 4-bit strings into the subsets, and it has a clearly defined inverse because we could go backwards just as easily, so therefore we'd say it's a bijection. So since it's a bijection, we could say that there's the same number of 4-bit strings with exactly 3 ones as there are subsets of size 3 out of a set of 4. Now we know how to find the number of subsets of a size 3 out of a set of 4. That would just be 4 choose 3. So we know that since there's this bijection, that's also the way we would find the number of 4-bit strings with exactly 3 ones. So we could say the answer would be 4 choose 3, and we could go ahead and find that answer, and we would end up, after canceling everything, with just a 4. I do want to say before I go on that this is how the book talked about coming up with the answer of these binary strings with exactly a certain number of ones in them, they said, let's look at this bijection. And that's something we can do. But actually, there's a way that you could more directly come to this answer here, 4 choose 3, because you could look at it this way, that this 4-bit string has 4 slots, right? But we want to fill 3 of them with ones. So we've got 4 slots, but we're going to choose 3 of them to put ones in. So it's a 4 choose 3 kind of thing, right? Just as if I'm saying I'm choosing 3 students out of a group of 4 students. It's the same thing as I'm just choosing 3 of the slots. Which slot? One, which of these slots do I want to choose out of a set of 4? So it's really a 4 choose 3 situation from the beginning. But the book does go through this bijection argument just to come up with that answer that way. So let's look at these questions. Not all of these questions are going to be ones that we need to use that bijection rule for, okay? So some of these are ones we can use, but find out the answer by using the product rule, okay? So a lot of these we already know how to do, but we'll see how, as we go down the line here, some of these we will need to use the bijection rule for. So first of all, how many strings of zeros and ones can be constructed with a length of 8? Okay, just a length of 8. Well, that would be where we just see it as a string of 8 characters, and we could look at it as choices. How many possibilities are there for the first slot, and how many for the second slot, and so on. And so there's 2 possibilities for each of those slots. So the product rule would just say that we multiply all of those together. So that would give me 2 to the 8th. Now, I want to say this, in your book, in the Xi books, when you answer questions like this, they're not going to make you take out your calculator and go 2 times 2 times 2 8 times, right? Or 2 to the 8th on your calculator. They just want to know that you knew how to get the answer. So they're going to be looking for you to to say the answer is 2 to the 8th. Okay. Again, we can always find that number, but we really don't care about that number at this point. Xibooks just wants to know, would you know how to get that number? So they would be looking for you to say the answer is 2 to the 8th. And the way you would do that in a Xibooks little entry box would be this: 2 with a caret and an 8. Okay, so that's what they would be looking for you to put in for an answer. So I just wanted to make that point right now. Okay, now let's go on to the next one. How many strings of zeros and ones can be constructed with a length of 8 if they all have to start with 101? Okay, if they all have to start with 101. Well, we could see it again as, this string of 8 characters, and we're going to have, a certain number of possibilities and use the product rule. But we already know what they need to start with. The first 3 numbers need to be zeros and ones. Digits need to be 0. The first 3 digits need to be 101. So we'll fill those out here and then realize that there are 5 slots left. So how many ways can we do that? Well, we'd have 2 possibilities for that first open slot, 2 for the next open slot, and so on. So there's 5 of those, so it would be 2 to the 5th. And again, if you were answering this for Xibooks, you'd say 2 and then the caret symbol and 5. Okay, let's go on to the next one. How many strings of zeros and ones can be constructed with a length of 8 if there must be exactly 3 ones? Now here's where we get to the new stuff, right? For just using the product rule, we can't get the answer, right? Because the 3 ones could be in different locations for all of these different ones. So we'd have to say, oh, wait, I just learned that if we've got binary strings and we have to have a certain exact numbers of ones, it would also work for a certain number of zeros too. But anyway, we just learned that if we're looking for a certain number of ones, then we can use that combination formula. So so I could say, well, it's a length of 8 and we need 3 ones in there. So we can find the answer by taking 8, choose 3. Now, let me say this before we go on, because I just thought of it right now. We've gone through this whole thing about the bijection, and so we just learned that, yeah, we can come up with a bijection between these strings and these subsets, and so therefore we were able to then know that we can use this formula, right? But honestly, we could actually go more directly to this 8, choose 3 by seeing it this way, that we're going to have 8 openings, and 3 of those openings need to have ones in them, and the others don't. So it's really just a matter of choosing 3 of those openings out of the 8, which comes back down to just subsets. Instead of choosing 3 students out of a group of 8 students, we're just choosing 3 spaces out of a group of 8 spaces. So anyway, I just wanted to say there's kind of a more direct route to go than what Zybooks brought up in being able to, see that, yeah, this would just be 8, choose 3. So 8, choose 3 would be 8 factorial over 3 factorial times 5 factorial, and then we would do some simplifying and get 56. Okay, now the last question. How many strings of zeros and ones can be constructed with a length of 8 if they have to start with 0, 1, and there must be exactly 3 ones? Okay, so we would realize that there's 8 slots, but the first 2 are already taken. We have a 0 and a 1. So we wouldn't have to worry about those, and we'd realize there's 6 slots left. But again, it's not just a matter of now they could be anything. There have to be exactly 3 ones. So we would know then, since there are 6 slots open and there need to be 3 ones, it would be, we need, oh yeah, we need, what do we need? We need 2 ones inside those 6 slots because we've already used up one of our ones, right? The first one was already there. So we're not even going to say it's 8, choose 3 because it would only be 2 now that need to be in the remaining slots. So it would be 8, choose 2. Oh, sorry, not 8. I'm sorry. It's not 8 because we had our first two slots taken up. So it's 6 slots. We need to get 2 ones within the 6 slots. So it's 6, choose 2. And so we could find the answer there. It ends up being 15. Okay, so just have to think through. I always just make a little picture like this so I can figure out what it comes down to and then find my answer. Okay, one more example here. How many strings of zeros and ones can be constructed with a length of 16 if the first half must have exactly 5 ones and the second half must have exactly 3 ones? Okay, so what I would do here is I really do this. I would write out all my slots there, and then if I did another one just like it, I wouldn't write out all the slots. But if it's something I'm thinking through fresh, haven't done it lately, I would go through this. I would put 16 slots there, and I would mark off the first half, and I'd put some notation there saying that there needs to be exactly 5 ones in there. And then the second half, there needs to be 3 ones in there. So once I get that picture, I'd say, okay, well, if it was just a matter of that first half, I could figure that out, right? Because there's there would be 8 slots in that first half, and 5 of them need to be won. So it would be 8 choose 5, right? And I could find that answer, and it would be ends up being 56. And then for that second half, now that's just for the first half, and we're going to have to do something with that later, but just hold that thought for a minute. Now for the second half, we have 8 slots and we have 3 ones, so it would be 8 choose 3, and we would get this. Notice that we get 56 again, and this is an example where, as we saw before, if the top is the same and the bottom to end up coming together to give the top. Here's a 5 over here on the left and a 3 underneath on the right. 5 plus 3 is 8. You know, if you have that relationship, we saw that we end up getting the same answer for those. And so we got 56 in both cases because it just involved, in both cases, a 3 factorial and a 5 factorial on the bottom. So that's why we got the same. Now, that doesn't give us the answer to our question, but it does tell us how many ways we could fill up the first half and how many ways we can fill up the second half, right? But let's think about it this way. Now we can consider it as thinking back to the product rule. We could say, how many ways can the first half be done? And then find out how many choices do we have for the second half to be done. And if you think about it, then the product rule would say, well, if there's this many, think about it as stages. And there's, in this stage here, there's 56 ways. And then this stage here, there's 56 ways. So the product rule says that you just multiply those numbers together. So there's how many ways for that first half to be done? 56. And then how many ways for the second one? 56. So multiply those together. And then you get the answer. I moved a little too quick. But anyway, I had on that last slide 56 times 56. Now, it's possible, I think, in a lot of the problems that you have to do with zyBooks, it'll tell you to leave your answers in terms of just the factors like that. So they might tell you that, say something like, put your answer in terms of, the factors or whatever. And so maybe for that one, it was 56 times 56. You might then need to put a 56 and a star for times, and then another 56. And again, we could find that answer, but they're mostly interested, and I would be mostly interested in knowing, do you know how to come up with the answer? So 56 times 56 would tell me you know. Okay, now this is an application that they have in the book, and I think it's interesting, so I thought I would talk about it. I don't think there's any questions about it. So, but I thought it was interesting enough that I wanted you to understand how something like this, we could use what we've just learned to answer a problem like this. So this says, consider a city whose streets are laid out as a grid. So they're either going perfectly north and south, or east and west. Streets run north-south or east-west. A visitor is dropped off by a cab at a certain intersection and would like to visit a museum that is 6 blocks to the east and 3 blocks to the north of his current location. The visitor always takes a direct path and never travels west or south in the course of his walk, meaning he's not going to go too far, too far north and then have to retrace his steps or come back down south. It's going to be a direct way, even though he can go there's several ways he can go about it. But he's not going to go out of his way to visit something way up north. That's what that's saying. Okay, then how many distinct paths are there for the visitor to walk to the museum? So you see this picture down here is, imagine him starting at the bottom, and he needs to get to the top here. And let's see, 6 blocks east and 3 blocks north. And if you count the blue arrows, those are going north. There's 3 of those, and then there's 6 going east. So this is one of the paths that would get him to the point where he needs to go. But you see, he could have done all 3 of the blocks north first and then just gone straight over east the rest of the way. But there's, of course, all kinds of possibilities. Okay, so what they say is that we could look at this situation and realize that we could come up with a bijection between these distinct paths and actual sequences of n's and e's. We could even put it down to zeros and ones like we've just been doing, but they're gonna, say, let's be different. Let's use e's and n's. And so I could imagine that I have a sequence of characters of length 9, and 6 of them need to be e's, and 3 of them need to be n's. So then we would be able to think, well, if that's the case, we've got 9 blocks, 9 characters, and 3 of them need to be n's. So we would just take 9, choose 3, right? Because that's the same problem as what we just did with the binary strings. If we had said zeros and ones, we'd be saying, how many different ways can we have 3 ones in a binary string of length 9? It's just the same thing, other than in this case, where how many ways can we have 3 n's in a string of length 9 when the only options are n's and e's. Okay, so anyway, I thought that was an interesting application, so I wanted to point it out so that you can see that there's maybe some situations where you wouldn't necessarily see them use this this thinking of combinations here, and yet you could use them. So in this video, we've already covered 2 sections. The one section on the bijection rule, where we also talked about the K-to-1 correspondence and the K-to-1 rule. And then we also had another section on counting subsets, where we learned that formula. But there's a third section for this lesson, and it's called, I think it's just called Subset and Permutation Examples. And it's there to kind of give you some practice and help you be able to distinguish the difference between questions that are going to be where you're going to be needing to find permutations, as opposed to questions where you're just finding subsets, or you might think of that as what we've said is combinations that we just talked about. So there's nothing new in here, but they just kind of help you learn how to distinguish. Is this a permutation problem, or is this a subset problem? Or in other words, is this a combination problem? So definitely read through that. There might even be some participation problems to do. I think there might be. So definitely read through so that you get, I'm not going to go over what they say in there because nothing's really new, but they're just kind of helping you see the difference. So normally I don't say be sure and read the zyBooks section because I tell you everything that's in there, but I'm going to leave it to you to read through it. It's pretty short. Read through it so that you can kind of get an idea how to distinguish between permutations and combinations, and then do go ahead and complete those participation activities for that section too.